All right, we have covered some background material up through kinematics in 1, 2, and 3 dimensions to get um, some ideas about motion. And now we're ready to connect those ideas together with actual laws of physics that explain why that motion takes the form that it does. So the material for introducing Newton's laws of motion is split between two chapters, chapters 5 and 6. We're going to meet things at a particular level here in chapter 5, and then in chapter 6 we're going to dive into a few topics at a little bit more depth that they deserve. Our main goal here is to become acquainted with Newton's 3 laws of motion and think about what they have to say and what they mean. And I got a couple whimsical images here to start off the chapter. We're here on the right is the Rube Goldberg device at the Children's Museum in Indianapolis, which I hope everyone has gone to see and played with. And if you have not, watch this thing move billiard balls around in a most peculiar way, you definitely should try to do it. It's a lot of fun. And then a Rube Goldberg device involving even a bird to automatically wipe your mouth after you've made a mess with your soup. So, Newton's laws of motion, the things that make all machines and all things go and move. So, as might seem appropriate, we're going to start off with Newton's first law of motion out of the three. Newton's first law of motion, most succinctly, is if the net force on an object is zero, the velocity of the object is constant, or the velocity of an object is constant if and only if the net force on that object is zero. So we take all of the forces acting on an object, add them all up as vectors. If they sum to zero, then the object is in equilibrium. And then its velocity, which is both speed and the direction that it's moving, are fixed. And it's equivalent to saying that the body can't accelerate. So acceleration has to be zero. There is a little bit like special language, or like the asterisk at the end, regarding the frame of reference that you're using to make these observations and statements about physics. Newton's first law is valid in an inertial frame of reference. You can generalize that, and that's a topic for later in physics in your physics career. The level that we're going to deal with things, you have forces in an inertial frame of reference. If those forces all add to zero, then you have the object's velocity remaining constant. So a few quick examples of what would be a non-inertial reference frame. If you had a reference frame that was accelerating up, in that frame of reference, it would appear like there is a fictitious force of gravity pulling everything down towards the floor in that reference frame. It's not actually a force causing that. It's just that the entire frame of reference is accelerating up. And you get similar things in a rotating frame of reference. You have fictitious forces for the Coriolis effect or the centrifugal force. So those are things that act like forces but appear because you have a reference frame that's accelerating. It's not foundational in the sense of Newton's first law of motion. Okay, let's try to get a little intuition for Newton's first law of motion, and in particular, try to get by some misconceptions with a couple questions. So you're a passenger in a car and not wearing your seatbelt. So stop, full stop right there. Don't do that. A good test of do you understand Newton's first law of motion is, do you always wear a seatbelt when you're in your car? You absolutely should. If the car stops without a seatbelt, there's nothing that's going to make you stop. You should understand that. All right, you're a passenger in a car, not wearing your seatbelt. Without increasing or decreasing its speed, the car makes a sharp left turn you find yourself colliding with the right-hand door, which is the correct analysis of the situation. Before and after the collision, there's a rightward force pushing you into the door. Starting at the time of collision, the door exerts a leftward force on you. Both of those statements are true. Neither of those statements are true. Think about which of those is correct, which of those makes sense in terms of Newton's first law of motion. Talk it over with your physics friends, and then when you are ready, restart the video. All right. So correct analysis of the situation based on Newton's first law of motion. You kept trying to move with a constant velocity while the car was accelerating. And it was not until the door ran into you and started pushing you to the left that your velocity changed. Okay. So you kept trying to move at a straight line, constant speed, while the car was turning around you. So starting at the time of the collision, the door exerts a leftward force on you. And then that force is what's making you turn along with the rest of the car. Yeah, let's try another one. A child is driving a bumper car at an amusement park. In that ride, she's traveling at the car's maximum speed when she crashes into a bumper attached to one of the sidewalls. During the collision, her glasses fly forward from her face. Which of the following statements best describes why the glasses flew from her face? So read through them all, give them all a good think. Which one of them makes sense in terms of Newton's first law of motion? Talk it over with your physics friends. And then when you have a consensus, let's unpause the video and go forward. All right. So really important to understand this. So all that happened was the glasses continued moving forward because there was not enough force to keep them attached to the girl's face. Okay. So they were not pushed off of her face. They just kept moving with the same velocity they had. And there's not enough force to make them accelerate, to slow down, to move along with the girl and her bumper car. Okay. We'll talk a little bit about non-inertial frames of reference, and then there's a video that'll be linked here that's is a nice, really nice demonstration, in my opinion, of what the Coriolis effect is. It's sort of in terms of everyday things, trying to play catch with a little basketball in a rotating frame of reference. But Coriolis force is responsible for a lot of the gross characteristics in our atmosphere and also in the oceans for the Earth. So we should talk about it a little bit. The Earth is a sphere, and it rotates as a solid body. And the point that is furthest away from the center of the Earth along the rotation axis is the part that's rotating fastest. So the rotation axis is straight line North Pole, South Pole through the center of the Earth. If you're at the North Pole, you're actually on the rotation axis. Same if you're at the South Pole. If you're at the equator, you're furthest out and you are making the biggest circle in a 24-hour period. So your velocity from rotating along with the Earth is greatest in magnitude at the equator. So you're rotating fastest towards the east at the equator. So now let's imagine what happens to like a little parcel of air where you throw a ball or something. So if I'm at the equator and I face north and I want to throw a ball, what's going to happen is as the ball is going northward, it is going faster to the east than the ground underneath it. So instead of going straight north on a rotating Earth, it's going to deflect over to the right. Similarly, if I'm at the equator and I want to throw a ball south, okay, so I throw the ball south, it is moving faster to the east than the ground underneath it. And so it's going to deflect. If I'm facing south, it's going to deflect to the left. Okay. These effects are termed the Coriolis force. We didn't really have to worry so much about the equation for it in this class, although the equation's not too bad. It just involves a little cross product. What this gives rise to is, for example, you have the pattern of circulation for hurricanes and storm systems in one hemisphere. The sense of rotation is different than in the other hemisphere due to the Coriolis effect. We also have regions where the prevailing winds are split into being like primarily where we live from west to east, but both north of us and south of us, they're going in the opposite direction, east to west. And that's because convection flows from the equator, where the air is hottest and hotter tries to rise. Those get split up by the Coriolis effect into separate bands of prevailing winds. All right, so big picture for our physics class, you do live on a Earth that is rotating. It's also revolving around the sun. It's doing all sorts of things. So it's not an inertial frame of reference, but it is close enough. You have to do fairly careful experiments for the sorts of things that we would do in a physics lab to tell that you're on a rotating planet and not in a strictly inertial frame of reference. So want you to be aware of what an inertial frame is, what a non-inertial frame is, but then for most things that we're going to be dealing with, unless otherwise noted, you can take your frame of reference to be an inertial reference frame. Okay, so let's try a question based on that idea in Newton's first law of motion. So you are sitting in a soundproof, windowless room, board a hovercraft, moving over flat terrain. Which of the following can you detect from inside the room? Rotation, deviation from the horizontal orientation, motion at a steady speed, acceleration, state of rest with respect to ground. And with what we know about Newton's first law of motion, which of these could you tell from within that very isolated, soundproof, windowless, frictionless hovercraft moving over flat terrain? Think about it. There could it be multiple answers that are correct? Think about what you think makes most sense in terms of Newton's first law of motion. Talk it over with your physics friends, and then when you're ready to go over the answer, unpause the video. All right, so things that you could tell, we'll talk about them. So inside our little hovercraft, with the hovercraft we're rotating, then if I'm playing a game of pitch and catch with a friend in the hovercraft, I would tell that the ball is going to be deflected. So we could tell if our frame of reference were rotating, because that involves an acceleration. Could we tell if there's a deviation from the horizontal? Yes. If the hovercraft were to tip, we would see things start to roll in a particular direction. So you can see the effect of basically the normal force not completely canceling out gravity because things are tilted. We cannot tell if there's motion at a steady speed. Okay. Every inertial reference frame is equivalent to every other inertial reference frame. So there's no way to tell if you're moving at a steady speed. And similarly, jump ahead to 5, there's no way to tell if you're at rest with respect to ground. Okay. You can tell if there's an acceleration. So one way to tell that, so let's say I have a ball on a string, and all of a sudden the hovercraft started accelerating in the forward direction. Well, what's going to happen is that ball is going to swing back. And it's going to swing back until the tension in the string provides enough force to make it accelerate forward along with the rest of the hovercraft and its contents. Okay, so you can tell if there's an acceleration, you can tell if it's tipping, so there's a deviation from the horizontal, you can tell if there's rotation. There's nothing you can do from within the frame of reference outlined in that question to tell if you're moving with a constant velocity or you're in a state of rest.